Welcome to this presentation about LEON5, our next generation high-performance fault-tolerant processor, and the ongoing developments using the LEON5. My name is Daniel Hellstrom. I'm working at the Geisler site in Sweden of CAES. I will give a brief background, some overview on the availability of this processor, and the main features of the processor and its radiation tolerance approach, virtualization support and the current status, where you can find that, and then the ongoing developments and a summary. And throughout the presentation there are some comparisons with our other processor called LEON5, which I will talk about on the sponsor presentation later on. On this slide you can see the 712 RC, which is our dual-core LEON3 fault-tolerant processor component. It's been around for approximately 10 years or so, and it's fault-tolerant by design, and it's radiation hardened through the technology. Our 740 microprocessor component offers a higher frequency and a higher performance in general compared to the 712. It's a quad-core LEON4 machine, and it's also fault-tolerant by design and radiation hardened by using ST's space process on 65 nanometers. It's different also when it comes to the architecture, where it has been improved with a common L2 cache and wider buses and a lot of more IOs, of course. For our next generation high-performance processors, we are designing two new IPs, the LEON5 and the NOEL5 processors. They are both targeting high-end FPGAs and ASIC designs. The LEON5 is a continuation of the Leon line of processors and are mostly backwards compatible on the software and IP level. They are using the same architecture, and it provides new major performance over the older Leon processors. The NOEL5, on the other hand, is compatible with the RISC-V open standard, so it can be used as a high-performance 64-bit machine, but it can also be used in 32-bit mode. So that's a configuration option. And I'm not going to talk so much about that, but as I said before, there will be some comparison in between those two processors throughout the presentation. Both are available in fault-tolerant versions, and both are available within our glib IP distribution, which is an open source IP library. But they are also available as a precompiled bit streams available for a couple of different FPGA boards, which you can download from our website and use directly. And the pre-compiled bit streams works also with our GRMON hardware debugger elevation version, so you can get started quickly there. The major improvement over the LEON4 processors are that the LEON5 is a dual issue machine. So the pipeline has been extended and can now execute up to 2 instructions per clock. This gives a much better performance, but there are also other architecture changes and updates. For example, it will be able to connect to a multi-bus architecture and then multi-port L2 cache. But there are also other improvements that we are currently working on, such as virtualization. The NOEL5 IP from us is a new processor design. It's not SPARC compatible, but instead it's compatible with the open RISC-V instruction set. It can be both 32 or 64-bit compliant, depending on a build time configuration. It offers approximately the same performance as a LEON5 because it also is a dual issue machine. It has also fault-tolerant features, and it's available in the glib IP core library. One of the benefits with this is that you can take advantage of the ever-growing RISC-V software ecosystem. The LEON5 offers a higher computational performance over earlier generations, but you can still use your software and the tools. It builds on the well-proven fault tolerance approaches of previous LEONs and even improves that further. On the right you can see a picture of a subsystem which includes the LEON5. So this is to simplify the designs, the new designs, where you can drop in a whole instantiation with interrupt controller, timer, and UART and debug modules and the basic blocks that you would need for all designs. But you can also, in existing designs, replace the LEON3 and 4 using only the CPU blocks. The dual issue pipeline is capable of executing 2 instructions per cycle. For that to work, of course, the pipeline must be fed with 2 instructions, which causes the cache architecture to change. And there are also other changes to the pipeline necessary to get this working. All versions of LEON5 comes with a small FPU, which we call non-FPU, but the high-performance GR-FPU has also been improved for LEON5, and this is also available. Now it supports subnormal numbers, and it has improved the timing on both FPU compares and branches. The design of the cache controller is similar to the LEON3 and 4. It has a write-through policy and a single cycle to access data and instructions. However, it uses physical tags rather than virtual in the cache. So that removes some of the data stored in the cache. And it also has a 4-entry deep store buffer so that you can store 4 32-bit words or 2 double words without locking the pipeline. The LEON5 also supports a tightly coupled memory with the same timings as the L1 cache. And it also features fault tolerance features on the SRAM. The processor is connected to an AMBA bus. It supports both 64 and 128-bit wide buses for a higher bandwidth, but you can also use it on a 32-bit bus, so you can drop it in to replace the LEON3. It uses the same cache coherency protocol using snooping to implement multiprocessing. Keep in mind for NOEL5 designs though that the NOEL5 is little endian, so you need to configure the bus in a little endian for the NOEL5. But glib has been updated to support that. We are currently working on a new bus architecture where we use striped buses. This is to increase the data throughput on the bus and also to improve on real-time performance where we can avoid some of the CPU interference between the CPUs. That is also coupled with several instantiations of the level 2 cache and also the new FD DDR memory controller having several ports, which each of the L2 caches are connected to a unique port. Thereby, if one CPU accesses a different address than the other, then it can reach the L2 cache and also the DDR controller without interfering the other CPUs. We already did a prototype work since before, which proved very successful, so this is something that we are looking for both for LEON5 and NOEL5. We continue to protect sensitive areas such as cache memories and register files and tightly coupled memories using error correction codes. In the past we used RTL-based error correcting codes in ASICs, but now we have improved the support also for the built-in ECC in the FPGA fabrics. That's available, for example, in the UltraScale and the Microchip RG4 and PolarFire FPGAs. Unlike the older Leon generations, we also have support for level 1 cache scrubbing. So there's a hardware scrubbing running in parallel to the software, and it will correct and find single event upsets and correct that. The older designs were based on having traps on errors to correct, or that you have manual scrubbing. The new processor IPs also implement a new custom error correction scheme used to protect the cache and tight couple memories. We have filed a patent for this new design. We also have in the roadmap to develop a new block level redundancy feature where we will be able to support technologies that doesn't protect their flip-flops and combinatorial logic as well. The NOEL5 processor implements the RISC-V extension, which provides virtualization acceleration in hardware. So during last year we were able to show that we can start the Xvisor hypervisor and have a Linux running as a VM inside of that. We are also involved in other activities that focuses on supporting hypervisors on our NOEL5. For the LEON5 on the other hand, which is a Spark compatible processor, the ISA does not include support for hypervisors. So in that case we need to come up with a specification ourselves. So that is something that we are doing this year. The principles are basically the same, but we need a hypervisor to protect different guest operating systems from each other and from the hypervisor itself. We also want to be able to assign register sets and interrupts and DMA channels to different guest OSs. You will find our processor roadmaps on our homepage through those links provided, where you can see the new functionality and when they will be available. This slide gives a brief overview of the software ecosystem for Leon and NOEL5 processors. We aim to provide the same software ecosystem for our space segment, but there are some differences, for example in the level of maturity and where you get the software components. We have recently added support for Zephyr, so we have BSPs both for NOEL5 and Spark architecture ports and BSPs for Spark. So there's a difference in the maintenance here, where on the Spark side we typically do the architecture ports, whereas on the RISC-V it's a matter of developing BSPs. So it's easier for customers to add support for custom operating systems and environments on their own. We've also continued to develop the Leon and Spark software support, but we're also adding hypervisor support. During 2021, we also improved the GCC toolchain. So we've added LEON5 optimizations to the backend on the Spark backend of GCC. And that's in order to take advantage of a bit more of the dual issue pipeline to arrange and schedule a bit better. But the support in old toolchains are quite good when it comes to taking advantage of dual issue machines. So GCC is already scheduling quite nicely for already when we started. I will present more on the software ecosystem as part of the sponsor presentation later on. We are involved in several different development activities with our LEON5 and NOEL5 IPs. Either we are concentrating on improving the architecture for the future, or we are working towards getting its silicon components. We have also completed the development of a demonstration chip on 28 nanometer technology. This demonstration chip includes both a LEON5 and NOEL5 processor. The LEON5 being a 32-bit and the NOEL5 is in a 64-bit configuration. It's a red hard technology from ST Microelectronics on the 28 nanometer node. So this has been a collaboration between ST and Geisler research and development teams. And so far we have seen very good results, and we reached well over 1 gigahertz on the LEON5. And currently we are doing a radiation characterization of the device. On the image you can see our radiation test board. That's the device has been soldered onto, and which we will use in the radiation test campaigns. We are also running other software and other things on it to test it. So the basic functionality of the ship has already been demonstrated. The test and demonstration ship will also be flying in space as part of the GOMEX-5 satellite mission. It's a CubeSat mission, and on one of the payloads the test ship are soldered onto. You can see the silvery part on the picture there to the right. The test ship is of course great, but what we're really working against is a GR765, which will be an 8-core LEON5 machine, our next generation high-performance microprocessor. And it looks quite similar to the GR740 in terms of I/O. It's just that some of the IPs we've improved, and for example CAN have now support for flexible data rates. There are more of the same IPs in some cases, and for example more ports, but we also have new IPs in here, high-speed serial links, space fiber in this case, and also we're looking into time-sensitive network on the Ethernet side. We are developing our own NAND memory controller to be put into this design, and there are new DMA units which are freestanding, not connected to any specific I/O. But the main thing also is the architecture, of course, which I've talked about before on the striped buses and the multi-port DDR2, DDR3 memory controller, and then of course the frequency of the processor device itself. And with all these I/Os, we needed more pins as well, so we've decided to look for and select a component which has more than the double number of pins than the 740. So with that, I wanted to conclude this presentation by saying that we have developed 2 different processors, the LEON5 and the NOVA5. Both are suitable for space applications, but they use 2 different instructions architectures, and with that there are differences in terms of reuse of existing software or third-party support and integration, and with other IPs, etc. So there are things to consider when selecting between those. The performance today are very similar because of the dual issue pipelines similarities, and we are committed to improving the Spark ecosystem and continuing supporting the existing ecosystems for the LEON line of processor a long time in the future. And as you see, we have planned also new LEON devices going forward. So I want to thank you for listening.